Okay, hey there, gang. Welcome back. Today, we are going to talk more about exponential functions. So on Thursday of last week, we introduced this new family of functions called exponentials. Today, what I want to show you, sorry, some papers here. Today, what I want to show you is how we use those functions to solve lots and lots of really interesting problems in the real world. I want to sort of highlight the differences between these functions and other functions we've played with, and then we're going to do a little activity. On the matter of the partial credit for the exam, some of you have the partial credit, and I think I'm in like the C's now, but the majority of you do not yet. So if you've been watching that and hoping that it would be there by today, I apologize, it's not in just yet, but I do have time set aside this afternoon to go in and finish that up. So your partial credit, if it's not in yet, will all be in by the end of the day today. Here we go. This is MAC1105, section number 015, which is college algebra. And the date today is the 22nd March 2022. Today, we're talking more about exponentials. It can be very tempting to look at this part of the course as kind of just a bucket load of formulas and procedures. And what I would like you to try and do is to see a little bit deeper than that. And to see how these things are connected to one another and how they're connected to the algebra rules associated with exponents. So maybe I'll begin by saying, recall that an exponential function is one of the form, call it f of x, and you're looking at some constant times some other constant raised to the power of x. The number c is sometimes called the initial value. And the number b is called either the base or the growth factor. Now I'm going to, like I said, introduce a few kind of special formulas here that can help you solve particular problems relating to exponential functions. Take a quick scan here and see if anything has changed in the MyOpenMath. I don't think it has, but we'll just go in and solve a handful of these problems. Yeah, okay. So the first thing I want to do is introduce this idea of growth rates. We talked about growth factors and how this is kind of similar to a slope. Remember we said last Thursday when we introduced these that linear functions are functions where every time x goes up by 1, the output has some constant added to it, right? And that constant that you add with a linear function is called the slope. With exponential functions kind of can be characterized similarly. And that this growth factor, this is the thing that you multiply the output by. This is the number that the output gets multiplied by every time the input goes up by 1. So a linear function, you add some constant to the output every time the input goes up by 1. That constant is called the slope. Exponential functions, you multiply the output by some constant every time x goes up by 1. So if you have a function that's, something times 2 to the x, then every time x goes up by 1, you're multiplying by 2. If you have something like, 3 times 5 to the x, every time x goes up by 1, the output gets multiplied by 5. One neat concept that's tied to this is something called a growth rate. And growth rates and growth factors are different, but they're connected to each other. Think back to those problems where you had to figure out a percentage, like the sale problem from the homework 2 weeks ago, the inverse functions sale problem. If you want to discount something by, say, 5%, that means you're going to multiply that price by 0.95, right? Because if you're taking 5% off, you're still paying 95% of the total. Or if I have some sort of loan where I'm charging you 5% interest every month, then every month I would take the balance and multiply by 1.05, because I want to add 5% onto that balance every month. And that 0.05 is the amount I'm adding. Those are examples. This pen is not good. Those are examples of growth rates. And also correct. Okay, so I think the easiest way to kind of introduce this, let me first just tell you what the thing is. So an exponential function something like f of x equals c times b to the x can be rewritten as f of x equals c times 1 plus r to the x, where b is equal to 1 plus r, and the number r is called the growth rate. All right. So if I were you, this would be sort of the first of the new recipes from today that I would tuck somewhere safely in my notes. R here can be positive and can be negative, right? If b is 1/2, then r is negative 1/2. If b is 1.3, then r is 0.3. So for any base b, you can always split it up as 1 plus something. And then that something is the growth rate. I think an example will make this pretty clear. Suppose, let's say, suppose suppose the price of gas is increasing at a rate of, let's say, 4% per week. Right now, gas costs, say, $3.90 per gallon. I'd like to do two things. Find a function modeling the price of gas X weeks later. And also, I'd like to find the price of gas, say, five weeks from now. So a little bit of critical thinking could get us there even without the formula. And I want to kind of walk you through that logic to help you understand where the formula comes from. And then we'll approach this as you might on an exam or something. So my function f of x here, let's call it f of x. This is the price of a gallon of gas X weeks from now. That's the idea. So I could say for sure what f of 0 is, because the problem told me what gas costs right now. Right now, gas costs $3.90. This would be, let's write this, 3.9. Think about the rabbits, right? Remember the problem we did with the rabbits? I'm doing the same sort of thing here to help us see where this formula is coming from. I'll show you how you would solve this quickly just using the formula, but this is mostly to help you see where the formula is coming from. F of 1 would represent the cost of gas 1 week from now. And I was told that gas prices are increasing at 4% per week. So what number do I need to multiply 3.9 by in order to get that price to go up by 4%? This is going to be 3.9 times what? Okay, maybe too much at once. Let me back up a little bit.
Is it 1.04?
Yes, it's 1.04, exactly. Because I want to pay 104% of what gas cost last week. I can justify this for you. So since it doesn't seem to be jumping out right away, next week, F of 1, that's the price of gas 1 week from now, should cost 4% more than what I'm paying previous week. So here's what I paid last week. And then 4% more, I'm going to add to that 3.9, 4% of 3.9, which is 3.9 times 0.04. And if you factor the 3.9 out, what's left in here is 1 plus 0.04, which is 3.9 times 1.04. Does everybody follow how I arrived here? This is the price last week. This is the 4% of the price last week. So I add these together to get my 4% growth, right? I said that the price of gas is increasing at a rate of 4% per week. So 1 week after we started, the price of gas should be the price of gas last week plus 4% of the price of gas last week. This is that 4% increase. And when you factor out the 3.9, add the 1 plus 0.04, you get 3.9 times 1.04. Let's apply this logic again. F of 2. This should be the price of gas last week plus 4% of the price of gas last week. So that's 3.9 times 1.04. That was the price of gas last week. Plus 4% of this number. So that's 3.9 times 1.04 times 0.04. This is the price of gas in week 1, which is last week. We're in week 2 now. And this is 4% of the price last week. You take the price last week, which is 3.9 times 1.04, and multiply by 0.04. This is 4% of the price last week. So I'm just increasing the price by 4% by adding 4% of the price last week to the price last week. And now if you factor 3.9 times 1.04 out, what you're going to get is 1 plus 1.04. This is 3.9 times 1.04 times 1 plus 0.04, which is 3.9 times 1.04 times 1.04 is 1.04 squared. And in this way, just repeating this, what you'll see is that x weeks later, we would have 3.9 times 1.04. Well, f of 1 had that to the 1, f of 2 has that to the 2, f of x will have that to the x. And we could have this is what we get just plugging C equals 3.9 and R equals 0.04 into the growth rate formula. Right? If I do that, the growth rate formula was f of x equals c times 1 plus r to the x. If you plug in 3.9 for c and 0.04 for r, this is this. So the fast way to solve this problem is just to take that growth rate formula I gave you on the previous page and plug in the initial value, right? How much gas costs at the start, and the growth rate for R. Pretty cool, huh? Okay. There was a part B to this. We wanted to know how much would gas cost? Was it 6 weeks from now, 5 weeks from now? 5 weeks from now. So f of x right here, here's my answer for part A. That tells me how much gas is going to cost X weeks from now. I want to know how much gas is going to cost 5 weeks from now. So this will be f of 5. F of 5, plug in here is 3.9 times 1.04 to the fifth power. And this number isn't super easy to compute, so again, we'll lean on my calculator, which is fine. When you type this stuff in, you need to be careful. So 3.9. We get 4.7449. I'll round that to 4.7. So if gas were increasing at 4% per week and starting at $3.90 per gallon, then 5 weeks later, we would be paying $4.74 per gallon. When you hear people on the news talk about how the economy is growing at 3% or 2% or whatever, this is what they're talking about. They're talking about this number right here. So that GDP growth, the type of growth that people like to talk about on the news, is exponential growth. And that number is the growth rate. Questions on growth rates? Everybody comfortable with how we can come up with this quickly? Just plugging into this formula. If I told you that the price of gas was going down 4% every week, what would you plug in for R here?
0.96.
So that would be our base. It's true that the base, the 1 plus R, would be 0.96, but what would we be plugging in for R specifically right here?
Minus 0.04.
Excellent, right? So if we're decreasing at a certain rate, that means R is negative, and you would plug that number, that percentage written as a decimal, into this formula. If you are increasing at a certain rate, you would find that percentage as a decimal and plug that into this formula. And remember, C is always your starting value, right? This is what you get when you plug in 0 for X, because this whole thing will become 1 when you plug in 0 for X. So C is always your starting value or your initial value. R is your growth or decay rate. If you're growing, R is positive. If you're decaying, R is negative. The next sort of special formula like this, I like to call the doubling time. So there are a lot of things in the real world whose growth can best be described by saying it doubles every so often, right? Like maybe the height of grass in my yard doubles every month or something. Or if I was very lucky, the money in my bank account might double every 10 years or something like that. If a quantity doubles every k units of time, and initially measures C, then X units of time later, it will measure next kind of special formula, C times 2 raised to the power of X over K. So C here is the initial amount. And K is called the doubling time. Sometimes you'll see this written with the variable t instead of the variable x, because usually your independent variable here is representing time. Either way is okay. The way this works is that if k is 1, imagine k here is 1, then this is like 2 to the x. It's like the rabbit problem. And every time x goes up by 1, the output gets multiplied by 2. If I have this x over k instead, then in order to multiply by 2, x needs to go up. I need this power to go up by 1. And in order to get x over k to go up by 1, it's not enough to make x go up by 1. You need to make x go up by k, right? If x is equal to k, then this power is 1. If x is equal to 2k, then this power is 2. If x is equal to 3k, then this power is 3. So this power increases by 1 every time x increases by k. And that means that this exponential multiplies by 2 every time x goes up by k. And that's what we wanted, right? We wanted some function which doubles the output every time the input increases by k. Let's grab this. I think you probably have a doubling time problem or two in your homework. That's a half-life, that was fun too. Control F. Oh, maybe not. Okay. Well, I have an example problem like this in our activity. We'll work through that one together. Since you don't have doubling time in your homework, but you do have lots of half-life, let's skip to that for now. Half-life and doubling time are very similar. The only difference is the base is 2 in doubling time, and it's 1/2 in half-life. Half-life is a concept from physics. We talk about radioactive decay. Over time, elements decay, something called beta decay, especially high energy elements that have a lot of neutrons in them. It's one of the ways that we can tell how old something is by measuring the amount of a certain isotope of carbon in it called carbon-14. Carbon-14 decays at a steady rate. So you can see how much carbon-14 has been lost compared to the original sample, and that'll tell you how old the thing is. We'll look at problems like that, but first let's go ahead and say what this is. So if a quantity halves every k units of time, and initially measures c, then x units of time later, it will measure f of x equals c times 1/2 raised to the power of x over k. And it's precisely the same logic. Every time x goes up by 1, or sorry, x goes up by k, that power goes up by 1. So every time x increases by k, this function multiplies by 1/2. C here is still called the initial value. And k here is called the half-life. Not to be confused with the excellent video game series from the late 90s and early 2000s. So let's take a quick example here. We'll do one of these from your homework. Okay, so they tell us that I'm going to go ahead and do question 7 here. The half-life for thorium 227, I don't even know if that's a real element, someone has to tell me better, is 18.72 days. And the amount A in grams of T 230. Why did I say 227, 239? I'm gonna have to assume that that's a typo. 227 after T years. From a 10G sample. It's what? And how much for only 8 grams is left? So let me modify this question just a little bit. They're giving us too much here. All right, and then and let's say how much is left. Yeah, here, let me. They're definitely giving us too much. So they told us the half-life. Let's split this into parts. Let's find a function a of t for the amount left after t days. Let's find the amount left after 2 months. Some unit conversion in. And let's find how long until, say, 8 grams left. Oh, and I crossed it out here, but we're beginning with a 10 gram. So, all right. Yeah, so the problem as it is in the homework, they're giving you a lot there to get started with, and I want to work up a little bit more than what they're asking for here. So I think this will be a better introduction to the concept. Also, if you look carefully there, there's a typo, right? They talk about thorium-227 here and thorium-239 here. I'll flag that for repair, but it should be thorium-227 throughout the whole problem. So where do I begin? If I want to find a function a of t for the amount left after t days, and I know that the half-life is 18.72 days, and that my initial amount is 10 grams, what am I going to plug into this half-life formula? What is C? What is K?
C is 10.
Very good. And K? So I'm going to write down the formula here without anything plugged in. C times 1/2. We're using the variable t here. Right? They asked for a function a of t. And then I heard correctly, C is 10. We're starting with 10 grams. What is K?
$18.72.
So K would be 18.72. So my function a of t, when I plug these things in, is 10 times 1/2 raised to the t divided by 18.72. I want to know how much is left after 2 months, right? So this is it. This is your answer for part A. We're done here. For part B, we want to know how much is left after 2 months. So what should I plug in for t? This is the amount that's left after t days. how much would be left after 2 months? Let's assume there's 31 months, 31 days in a month.
Would you plug in 62 for t?
Exactly. Right, so we have to be mindful of the units here. I wouldn't plug in 2 for t because this is 2 months, and my function tells me how much is left after t days. So 2 months means we're talking about t equals 62 days. So there will remain a of 62, which is 10 times 1/2 raised to the 62 over 18.72. That's how much thorium will be left. And like many of these things, the calculations are a little bit unpleasant. You cannot really do this nicely by hand, and you need to be careful with your parentheses. It's only the 1/2 that's being raised to this weird power. So we would type this in as on 10 times parentheses 1/2 close parentheses raised to, and then you, if you're working on an older calculator or just good discipline, would be to put this power in parentheses as well. 62 divided by 18.72, close the parentheses in the power, blam, we get 1.006, very, very little, almost nothing left. I'll round up to 7. Any questions about this calculation? Let's go ahead and answer part C. This is a slightly tougher one. We want to know how long until only 8 grams remain. This is going to point to us solving an equation. A of t, this function here tells me how much thorium is left after t days. So this is the amount of thorium left after some amount of time has passed. I want to know when will there be 8 grams left. So I need to set this equal to 8 and try to solve for t. Meaning A of t is equal to 8. And this is a new kind of equation for us. Let me go ahead and put in what A of t is. That's 10 times 1/2 raised to the t divided by 18.72 equals 8. We've never seen an equation like this before, so this is an exciting moment for us. This is our first exponential equation, and they're not easy to solve. The general tool for solving equations like this is something called a logarithm, and we're going to get to those soon, not today. For us right now, we can, so this exponential equation requires logarithms to solve by hand, because the variable is up here in the power. We've never actually seen an equation like that. We've seen lots of stuff like x squared equals 8, or x squared minus x plus 10 equals 0. But we've never seen anything where the x or the t or the thing you're trying to solve for is up in a power. And there's no nice algebra tool that'll get rid of that. I could divide both sides by 10 if you want to. And that would give me 1/2 to the t over 18.72 equals 8/10. But you see, there's no nice way to get the variable t down out of the power. So what we need to do is solve this graphically. Right now, this is all we have. I'm going to take the original equation, 10 times 1/2 raised to the t over 18.72 equals 8. And I'm going to show you how to solve this graphically. We solved some equations graphically at the start of the semester. What you do is you graph this function, y equals this thing. You treat this as a function. You graph y equals 8. And you look for the point where this graph hits this graph. So I'm going to bring up my calculator. I'd like you all to do this with me. And then after this, we're going to pivot to the activity. I'm going to type 10 times parentheses 1/2 close parentheses raised to the, and now our calculator, we have to use the variable x. So raised to the parentheses x divided by 18.72 in a graph. And we'll see here the graph of this function. We might want to play with our window settings a little bit, right? Because it's getting cut off at the top. I know I'm not interested in negative y values. We learned that last time, that exponential functions are always positive. Oh, so let's change my y max to 20 and my y min to like -1 or something. We can graph again. Now we'll see a little bit better what's going on. So here is that exponential function. If we zoomed way out, you would see it has that same shape that all the decaying exponentials have. But I'm looking for an intersection point with that thing and the line y equals 8. And I see it. It's right over here. I can use the trace function on the calculator to try and get an idea. So where is y exactly equal to 8? Well, it looks like it's somewhere around 5.7, right? Here y is 8.08. So that's almost that intersection point, 8.02, so that's 5.95. And by the time we get to 6.1, we've gone too far. So it looks like it's somewhere around 5.9. I'm going to sketch these really quickly. Here's the function a of t. Like this. Same decaying exponential shape. And here's the line y equals 8. And this intersection point appears to be happening when x is like 5.9. Or sorry, t. T is about equal to 5.9. And we can check with our table, see if we can get any better, but I would be okay with this. So I'd say here, so graphically, solution is approximately t equals 5.9. And we can try to get more precise, again, by playing with the table. So if I come in here, table settings, we'll say start the table at 5 and take steps of like 0.1. And we can see what we get. Second graph for the table. As we scroll down, these should get smaller, and 5.9, maybe 6 appear to be the closest, where this guy is exactly equal to 8. And if we wanted to get more granular, we could change the table settings to go up by a smaller amount, like 0.01, and then we can get really nerdy about it. But there's not a lot of sense in being super duper picky about these because we will develop the tools, the logarithm tools that we need in order to solve these equations exactly quite soon. So here I'd say 6.02, 6.01. Yeah, 6.02 is actually more careful. The table function, we get is approximately, let's say 6.02 looks like the closest. Okay, and you can get it again as granular as you want with this by changing the table settings. The window settings I used here were just -10 to 10 for x, the standard, and then -1 to 20 for y. That was the. And then to go hunting for that solution, right, in my table, to go hunting for that solution in my table, what I did is I went to the table settings, that second window. I told the table to start originally at 5 and to increase by 0.01 each time I go down. And that allows me to look with that level of precision, right? With the accuracy of 0.01 in the table for this solution. So you see every time I take a step down, the x goes up by 0.01. Alrighty, let's go ahead and pivot over to the activity. I want to make sure we have time enough to do that. So please go ahead and grab out your activity if you're able to print it. Otherwise, go ahead and pull this up. If you haven't pulled it up already, come here, the announcements, go to the announcement for today's class, and there is a attachment here. Go ahead and open this or pull it out if you printed it. I'm going to assign everybody to breakout rooms in just a moment. First, let me walk you through the problems. So problem 1 here, we've got an element, we call it magnesium. It has a half-life of 7 years. I'm saying if we start with a 22 kilogram sample, how much will remain after 3 years? For both of these problems on the first page, you need to first find the function that models the relevant quantity. So your function here should have a variable in it, either x or t, right? You shouldn't be plugging everything in. You're going to use the half-life formula that I gave you. That's the fastest way to do this. So you're starting with 22 kilograms, and we're told that the half-life is 7 years. So here, give me a function that tells me how much is left after x years or t years. Then you're going to tell me exactly how much will be left after 3 years by plugging in the appropriate amount for that variable. Second problem, population of squirrels at Squirrel Ridge Park has been doubling every 3 months. So this is a doubling time problem. We're told that the doubling time is 3 months, and we're starting with 250 squirrels in the park. If we assume that no squirrels die, right, none of them are going away, how many will be in the park 2 months from now? So again, I want you to tell me the function that models the number of squirrels, either x or t months later. It'll be a doubling time thing. And then separately from that, so function goes here, then separately from that, I want you to tell me how many squirrels are going to be in the park 2 months later. The last 2 problems here are quick graphing problems. I want you to sketch, ooh, this should be an x, not a t. Sketch for me these 2 exponential functions, right? One is 3 times 2 to the negative t. The other is 2 times 3 to the positive t. And you can use your calculator if you want, but make sure that you label at least 3 points. Make sure you draw in the asymptotes and label them. Make sure you draw in any intercepts and label them clearly. All right. Any questions on this? Okay, then I'm going to go ahead and assign breakout rooms. I'm going to be coming in to check and make sure you guys are actually working on these and answer any questions. We're going to do this for the next 15-ish minutes. Here we go. All right, once you get the invite, please go ahead and join. Hey guys, please go ahead and join your breakout room so you can help your group with the activity. And if you don't do that, I cannot give you credit. Well. That's a Hey guys, how's it going?
Trying. To see the years or the weight.
So C is always the kind of initial amount. It's the amount that we're starting with. So on the first problem, C would be the amount of magnesium we have at the start. So that's the 22 kilograms, the mass.
Okay, thank you.
Mhm. Okay, are my other folks here? Is there somebody else want to start on maybe problem 2 while Julian's working on problem 1?
I'm just knocking out the graph ones quick first because that's the fastest ones you could do.
Sure. Yeah, I think that's a fine strategy. Any ideas how we could get the first graph, the 2 to the minus t1? It's a little different than how we've seen these in class. There might be an algebra step there that can make life simpler. Definitely, we can plug into our graphing calculator. That's always an option.
For one, to get rid of the negative exponent.
Say that one more time.
You're talking about the negative exponent, the negative
exactly.
t. You can put it over 1.
Very good. Yeah, I can write this as 3 times 1/2 to the t. All right. So 2 to the negative t, you can think of this as like 2 to the negative 1 to the t, and that is 1/2 to the t. And that will definitely help. I think that'll make life a little easier. Now you can see what your base is, right? Your base is 1/2, or your decay factor, if you like to call it. Okay. Lexus, Haley, Destiny, anything you guys would like help with?
Yeah, I'm not really sure how to do these, to be honest.
Which one would you like to look at?
Any one of them. I just haven't caught on to how to do these.
Okay, let's look at problem 2 here, right? So they tell us that the population is doubling every 3 months. So this is like the doubling time thing. They've told us that we've got something that's going to double every so often. So we have here a doubling time problem, and the sort of quick way to solve these is to use that doubling time formula. And remember, C here is the initial amount, the starting amount, and K is the time to double. So if they told us that the population starts out with 250 squirrels, that means C is 250. And they told us that the population doubles every 3 months, that means K would be 3. So we can start with our function here, plugging 250 for C and 3 for K. And that would be part A. That's it. All we got to do. So part A, finding the function that models the population. Here it is. So that's the first part, right? That's the function. And then to figure out the population in 2 months, we would have to plug in some appropriate number for X here. And think about the units we're using. I'll let you think on that for just a minute. And then Destiny and Haley, is there a part of this that you guys wanted to grind on?
I think what you just explained helped it make sense a little bit.
Okay, good. Good. How are you feeling, Destiny?
I'm still trying to catch on, but I'm working on it.
Okay, I'll try talking with your classmates here. I think some of this is starting to click, and that's the trick. So everybody chat with each other for a minute. I'm going to check in on another room, and then I'll come back. Hey guys, how are we doing?
I finished.
Oh, nice. All right. Can you walk me through just a little bit of this, or maybe help walk your classmates through a little bit? Maybe the first problem there. How do we do that?
Sure, I plugged it into the formula and did 22 times 1/2 x over 7. Well, to the x over 7. And then I plugged in the 3.
Excellent.
Ended up with 16.34 approximately.
That sounds perfect. So we're told that the half-life is 7 years, and that we're starting with a 22 kilogram sample, right? So C, just like with the doubling time problem, C is the initial amount, and K here is the half-life. So our function would be 22 times 1/2 to the x over 7, and that would be the answer to our first part. And then since Samantha got us here, maybe I could ask somebody else, Eden, Gabriella, or Emily, to explain how we're going to find the amount left after 3 years. So what would I do with this function we just found in order to see how much magnesium is left after 3 years?
Wouldn't you plug in the 3?
So after 3 years, we would expect there to be F of 3 kilograms left. That means we have to compute this number, 22 times 1/2 to the 3/7. And we get about 16.3, like Sam did. What would this be measured in? 16.3 what?
Kilograms?
Yeah, very good, right? This 22, this is 22 kilograms. This number doesn't have any units. So this is 22 kilograms times this number is 16.3 kg. Excellent. Alrighty, I'll let you guys wrap things up. Make sure everybody is comfortable with these. If you've already finished, I think the nice thing to do would be to help your classmates a little bit with one that they're stuck on. Definitely take a look at those graphing problems. And then I'll pull everybody back in a minute or two. Alrighty, guys, how are we doing?
We're good. We're on question
3 now.
Okay, cool. I have a little tip for question 3. So definitely you can use the calculator, and the calculator will give you a nice graph. But if we want to kind of put this in the context that we've been talking about these things, one little tip that we can think of 2 to the negative t as 1/2 to the positive t. So if we want to, we can rewrite this function in this way, because remember that negative tower, that's the same as having like a 2 to the negative t, it's 2 to the negative 1, all to the positive t. And then that 2 to the negative 1 is 1/2. So if you want to, you could rewrite it this way. And then we see, oh, okay, the base is between 0 and 1, right? The base is smaller than 1. So this has to be a decaying exponential. C, that initial value here is 3. So I expect a graph looking something like all of those decaying exponentials. I wanted to find some points on this guy. Maybe the y-intercept and the points at -1 and +1. How would I find those? Oops, sorry, this is not up to me.
Wait, what are we looking for again?
Oh, so
Points.
curious, yeah. If I wanted to find the y values at these 3 points here at -1, 0, and 1, how would I find those?
Oh, I don't know. I was doing the calculator before, so a little.
That's okay. No, and there's nothing wrong with that. All I asked you to do is sketch the graph. So if you use the calculator to sketch the graph, that's fine. Just for fun, if I want to find the y values here, then I can plug these x values, or I guess t values, into the function. So f of -1, that would be 3 times 2 raised to the -1. And that's 3 times 2 to the, well, -1, that's +1. That's just 3 times 2, or 6. So this point right here, if I wanted to, if I wanted to label it, I could label it as -1, 6. That's a nice thing to be able to do, right? Because some questions give us the graph and then they ask us for some information. So if we can go from the points to the statement about the function or vice versa, it's a great skill to have. To find the y value of the y-intercept, remember we always just plug in 0 for our variable. So that means I'm looking at f of 0, that would be 3 times 2 to the -0. -0 is the same as 0 though, so that's just 3 times 2 to the 0. And 2 to the 0 is 1, so that's 3 times 1. So my y-intercept here is at 0, 3. And one neat thing about these exponential functions is that the constant c here is going to tell you your y-intercept consistently. As long as this variable doesn't have any funny business like t + 1 or t - 5, then this will always be your y-intercept. And then finally, if I wanted to find this guy, I would plug in 1 for t. That would give me 3 times 2 to the -1, which is 3 times 1/2. And you could think of that as 3/2 or 1.5. So this would be the point 1, I'll write it as a decimal. I think I'm generally a little more comfortable with those, right? So this would be a lovely graph. The only thing I might want here that I don't have yet, we asked you to label the intercepts and also the asymptote. What's the equation for this horizontal asymptote? Maybe I'll say, look back at those notes from last Thursday when we talked generally about the graphs of exponential functions. They all had the same horizontal asymptote. I'm going to go ahead and group everybody back into the main room so we can talk about these together for just a second, and then I'm going to let you guys go.
You're muted, by the way, if you're trying to talk.
Thank you. I always forget that it mutes when we come back. So I wanted to talk just briefly about one of these graphing problems with everybody here. The first graphing problem, we wanted to sketch the graph of f of t equals 3 times 2 to the negative t. And I think a useful trick, if you've been following along with what we've been doing in class, is to rewrite the 2 to the negative t as 1/2 to the positive t, because this way you can see what your base is. So the base here is 1/2. And the reason this works is because 2 to the negative t, that's the same as 2 to the negative 1 all to the t. And then that 2 to the negative 1 is 1/2. So we can rewrite our function like this. And this helps me see the base. B is 1/2, which is smaller than 1. So this is a decaying exponential. And once you know that, you can draw the graph shape. You know that all decaying exponentials have a graph that looks like this. To find specific points on the graph, you can plug in x values, or t values, I suppose, here. The one thing I didn't get a chance to talk about with anybody in the breakout rooms is this horizontal asymptote. This is the line y equals 0. You may remember from our class last Thursday. If not, now's a good time to stick it in your brain, that all of these kind of exponential functions, if it's just some constant times some other constant to a variable, all of those have the same horizontal asymptote. It's always the line y equals 0. Decaying exponentials approach it over here on the right. Growing exponentials approach it on the other side, on the left. So I'm going to go ahead and wrap up here for today. Thank you guys for the work you put in on this activity. If you didn't get to solve all of the problems here right now, that's okay, but please take the time to solve them and understand them. I have an office hour from 11 to 12 today. If you want to come talk about those or anything else, you're welcome to do that. And next time, we're going to talk a little bit more about exponentials, but mostly we're going to be getting into logarithms. So I'll have a tiny
What
bit.
time's your office hour tomorrow?
1 to 2.
Okay.
So
Thank
Tuesday
you.
is always 11 to 12. Monday, Wednesday, Friday, always 1 to 2.
Okay.
All right. So that's it. Next time, a tiny bit more exponentials and then logarithms. And remember what we said about logarithms. The key to getting through that part of the class, which is for most people the hardest part of the class, is to study exponentials. Make sure you do all the homeworks and quizzes, and to study the inverse function stuff. Make sure you really understand those two things. So if there's anything you want to talk about or anything I can help you with, please come ask, talk to me. Make sure you're familiar with and remember everything from inverse functions, and make sure you're fresh with the material from exponential functions, things like domain, range, asymptotes, all the stuff we talked about on Thursday of last week. Sure, Haley, I can take a quick peek at that. All right. That's it from me for today, guys. I hope everybody has a lovely rest of your day. Work hard on that homework set, and I will see you on Thursday.